An atomic clock is a clock device that uses an electronic transition frequency in the microwave, optical, or ultraviolet region of the electromagnetic spectrum of atoms as a frequency standard for its timekeeping element. Atomic clocks are the most accurate time and frequency standards known, and are used as primary standards for international time distribution services, to control the wave frequency of television broadcasts, and in global navigation satellite systems such as GPS. The principle of operation of an atomic clock is not based on nuclear physics, but rather on atomic physics. It uses the microwave signal that electrons in atoms emit when they change energy levels. Early atomic clocks were based on mazes at room temperature. Currently, the most accurate atomic clocks first cool the atoms to near absolute zero temperature by slowing them with lasers and probing them in atomic fountains in a microwave fill cavity. An example of this is the Nist F1 atomic clock, one of the U.S.'s national primary time and frequency standards. The accuracy of an atomic clock depends on two factors. The first factor is temperature of the sample atoms. Colder atoms move much more slowly, allowing longer probe times. The second factor is the frequency and intrinsic width of the electronic transition. Higher frequencies and narrow lines increase the precision. National standards agencies in many countries maintain a network of atomic clocks which are intercompared and kept synchronized to an accuracy of 10⁻⁹ seconds per day. These clocks collectively define a continuous and stable time scale, International Atomic Time. For civil time, another time scale is disseminated, Coordinated Universal Time. UTC is derived from TI, but approximately synchronized, by using leap seconds, to UT1, which is based on actual rotation of the Earth with respect to the solar time. History. The idea of using atomic transitions to measure time was suggested by Lord Kelvin in 1879. Magnetic resonance, developed in the 1930s by Isidore Rabi, became the practical method for doing this. In 1945, Rabi first publicly suggested that atomic beam magnetic resonance might be used as the basis of a clock. The first atomic clock was an ammonia maser device built in 1949 at the U.S. National Bureau of Standards. It was less accurate than existing quartz clocks, but served to demonstrate the concept. The first accurate atomic clock, a cesium standard based on a certain transition of the cesium-133 atom, was built by Louis Essen and Jack Parry in 1955 at the National Physical Laboratory in the UK. Calibration of the cesium standard atomic clock was carried out by the use of the astronomical time scale ephemeris time. This led to the internationally agreed definition of the latest SI second being based on atomic time. Equality of the ET second with the SI second has been verified to within 1 part in 1010. The SI second thus inherits the effect of decisions by the original designers of the ephemeris time scale, determining the length of the ET second. Since the beginning of development in the 1950s, atomic clocks have been based on the hyperfine transitions in hydrogen-1, cesium-133, and rubidium-87. The first commercial atomic clock was the Atomicron, manufactured by the National Company. More than 50 were sold between 1956 and 1960. This bulky and expensive instrument was subsequently replaced by much smaller rack-mountable devices, such as the Hewlett-Packard Model 5060 cesium frequency standard, released in 1964. In the late 1990s, 4 factors contributed to major advances in clocks: laser cooling and trapping of atoms, so-called -S Fabry-Perot cavities for narrow laser line widths, precision laser spectroscopy, convenient counting of optical frequencies using optical combs. In August 2004, Nist scientists demonstrated a chip-scale atomic clock, According to the researchers, the clock was believed to be 1/100th the size of any other. It requires no more than 125 milliwatts, making it suitable for battery-driven applications. This technology became available commercially in 2011. Ion trap experimental optical clocks are more precise than the current cesium standard. In 2016, NASA plans to deploy the Deep Space Atomic Clock, a miniaturized, ultra-precise mercury ion atomic clock, into outer space. The DSAC is considered much more stable than other current navigational clocks. Mechanism. Since 1967, the International System of Units has defined the second as the duration of 9,192,631,770 cycles of radiation corresponding to the transition between two energy levels of the cesium-133 atom. In 1997, the International Committee for Weights and Measures added that the preceding definition refers to a cesium atom at rest at a temperature of 0 K. This definition makes the cesium oscillator the primary standard for time and frequency measurements, called the cesium standard. The definitions of other physical units, e.g., the volt and the meter, rely on the definition of the second. The actual time reference of an atomic clock consists of an electronic oscillator operating at microwave frequency. The oscillator is arranged so that its frequency-determining components include an element that can be controlled by a feedback signal. The feedback signal keeps the oscillator tuned in resonance with the frequency of the electronic transition of cesium or rubidium. The core of the atomic clock is a tunable microwave cavity containing a gas. In a hydrogen maser clock, the gas emits microwaves on a hyperfine transition. The field in the cavity oscillates, and the cavity is tuned for maximum microwave amplitude. Alternatively, in a cesium or rubidium clock, the beam or gas absorbs microwaves and the cavity contains an electronic amplifier to make it oscillate. For both types, the atoms in the gas are prepared in one electronic state prior to filling them into the cavity. For the second type, the number of atoms which change electronic state is detected and the cavity is tuned for a maximum of detected state changes. Most of the complexity of the clock lies in this adjustment process. The adjustment tries to correct for unwanted side effects, such as frequencies from other electron transitions, temperature changes, and the spreading in frequencies caused by ensemble effects. One way of doing this is to sweep the microwave oscillator's frequency across a narrow range to generate a modulated signal at the detector. The detector's signal can then be demodulated to apply feedback to control long-term drift in the radio frequency. In this way, the quantum mechanical properties of the atomic transition frequency of the cesium can be used to tune the microwave oscillator to the same frequency, except for a small amount of experimental error. When a clock is first turned on, it takes a while for the oscillator to stabilize. In practice, the feedback and monitoring mechanism is much more complex. A number of other atomic clock schemes are in use for other purposes. Rubidium standard clocks are prized for their low cost, small size and short-term stability. They are used in many commercial, portable and aerospace applications. Hydrogen masers have superior short-term stability compared to other standards, but lower long-term accuracy. Often, one standard is used to fix another. For example, some commercial applications use a rubidium standard periodically corrected by a global positioning system receiver. This achieves excellent short-term accuracy, with long-term accuracy equal to the U.S. national time standards. The lifetime of a standard is an important practical issue. Modern rubidium standard tubes last more than 10 years, and can cost as little as $50. Cesium reference tubes suitable for national standards currently last about 7 years and cost about $35,000. The long-term stability of hydrogen maser standards decreases because of changes in the cavity's properties over time. Modern clocks use magneto-optical traps to cool the atoms for improved precision. Physics package realizations. A number of methods exist for utilizing hyperfine atomic transitions. These methods, with their respective benefits and drawbacks, have influenced the development of commercial devices and laboratory standards. By tradition, the hardware that is used to probe the atoms is called the physics package. Atomic beam standard. The atomic beam standard is a direct extension of the Stern-Gerlach atomic splitting experiment. The atoms of choice are heated in an oven to create gas, which is collimated into a beam. This beam passes through a state selector magnet A, where atoms of the wrong state are separated out from the beam. The beam is exposed to an RF field at or near the transition. The beam then passes through a space before it is again exposed to the RF field. The RF field and a static homogeneous magnetic field from the C field coil will change the state of the atoms. After the second RF field exposure, the atomic beam passes through a second state selector magnet B, where the atom state being selected out of the beam at the A magnet is being selected. This way, the detected number of atoms will relate to the ability to match the atomic transition. After the second state selector, a mass spectrometer using an ionizer will detect the rate of atoms being received. Modern variants of this beam mechanism use optical pumping to transition all atoms to the same state rather than dumping half the atoms. Optical detection using scintillation can also be used. The most common isotope for beam devices is cesium, but rubidium and thallium are examples of others used in early research. The frequency errors can be made very small for a beam device, or predicted in such a way that a high degree of repeatability and stability can be achieved. This is why an atomic beam can be used as a primary standard. Atomic gas cell standard. The atomic gas cell standard builds on a confined reference isotope inside an RF cavity. The atoms are excited to a common state using optical pumping. When the applied RF field is swept over the hyperfine spectrum, the gas will absorb the pumping light, and a photodetector provides the response. The absorption peak steers the flywheel oscillator. A typical rubidium gas cell uses a rubidium lamp heated to 108 to 110 degrees Celsius, and an RF field to excite it to produce light, where the D1 and D2 lines are the significant wavelengths. An 85 RB cell filters out the D1 line so that only the D2 line pumps the 87 RB gas cell in the RF cavity. Among the significant frequency pulling mechanisms inherent to the gas cell are wall shift, buffer gas shift, cavity shift and light shift. The wall shift occurs as the gas bumps into the wall of the glass container. Wall shift can be reduced by wall coating and compensation by buffer gas. The buffer gas shift comes from the reference atoms which bounce into buffer gas atoms such as neon and argon. These shifts can be both positive and negative. The cavity shift comes from the RF cavity, which can deform the resonance amplitude response. This depends upon cavity center frequency and resonator Q value. Light shift is an effect where frequency is pulled differently depending on the light intensity, which often is modulated by the temperature shift of the rubidium lamp and filter cell. There are thus many factors in which temperature and aging can shift frequency over time, and this is why a gas cell standard is unfit for a primary standard, but can become a very inexpensive, low-power and small-size solution for a secondary standard, or where better stability compared to crystal oscillators is needed, but not the full performance of a cesium beam standard. The rubidium gas standards have seen use in telecommunications systems and portable instruments. Active maser standard. The active maser standard is a development from the atomic beam standard in which the observation time was incremented by using a bounce box. By controlling the beam intensity, spontaneous emission will provide sufficient energy to provide a continuous oscillation, which is being tapped and used as a reference for a flywheel oscillator. The active maser is sensitive to wall shift and cavity pulling. The wall shift is mitigated by using PTFE coating to reduce the effect. The cavity pulling effect can be reduced by automatic cavity tuning. In addition, the magnetic field pulls the frequency. While not being long-term stable as cesium beams, it remains one of the most stable sources available. The inherent pulling effect makes repeatability troublesome and does prohibit its use as being primary standard, but it makes an excellent secondary standard. It is used as low-noise flywheel standard for cesium beam standards. Fountain standard. The fountain standard is a development from the beam standard where the beam has been folded back to itself such that the first and second RF field becomes the same RF cavity. A ball of atoms is laser-cooled, which reduces black body temperature shifts. Phase errors between RF cavities are essentially removed. The length of the beam is longer than many beams, but the speed is also much slower such that the observation time becomes significantly longer and hence a higher Q value is achieved in the Ramsey fringes. Cesium fountains have been implemented in many laboratories, but rubidium has even greater ability to provide stability in the fountain configuration. Ion trap standard. The ion trap standard is a set of different approaches, but their common property is that a cooled ion is confined in an electrostatic trap. The hyperfine region of the available electron is then being tracked similar to that of a gas cell standard. Ion traps have been used for numerous ions. 199 Hg+ was an early candidate. Quantum logic spectroscopy of a single Al ion became the most precise in 2008. In 2010, an improved setup using a Mg+ logic ion instead of B was demonstrated. Power consumption. The power consumption of atomic clocks varies with their size. Atomic clocks on the scale of one chip require less than 30 mW primary frequency and time standards like the United States time standard. Atomic clocks Nist F1 and Nist F2 use far greater quantities of power. Evaluated accuracy. The evaluated accuracy UB reports of various primary frequency and time standards are published online by the International Bureau of Weights and Measures. Several frequency and time standards groups in 2015 reported UB values in the 2 × 10⁻16 to 3 × 10⁻16 range. In 2011, the NPLCS-F2 cesium fountain clock operated by the National Physical Laboratory, which serves as the United Kingdom primary frequency and time standard, was improved regarding the two largest sources of measurement uncertainties, distributed cavity phase and microwave lensing frequency shifts. In 2011, this resulted in an evaluated frequency uncertainty reduction from UB equals 4.1 × 10⁻16 to UB equals 2.3 × 10⁻16, the lowest value for any primary national standard at the time. At this frequency uncertainty, the NPLCS-F2 is expected to neither gain nor lose a second in about 138 million years. The Nist F2 cesium fountain clock operated by the National Institute of Standards and Technology was officially launched in April 2014, to serve as a new U.S. civilian frequency and time standard, along with the Nist F1 standard. The planned UB performance level of Nist F2 is 1 × 10⁻16. At this planned performance level, the Nist F2 clock will not lose a second in at least 300 million years. Nist F2 was designed using lessons learned from Nist F1. The Nist F2 key advance compared to the Nist F1 is that the vertical flight tube is now chilled inside a container of liquid nitrogen, at -193 degrees Celsius. This cycled cooling dramatically lowers the background radiation and thus reduces some of the very small measurement errors that must be corrected in Nist F1. The first in-house accuracy evaluation of Nist F2 reported a UB of 1.1 × 10⁻16. However, a published scientific criticism of that Nist F2 accuracy evaluation described problems in its treatment of distributed cavity phase shifts and the microwave lensing frequency shift, which is treated significantly differently than in the majority of accurate fountain clock evaluations. In March 2014 and March 2015, the Nist F2 cesium fountain clock reported a UB of 1.5 times 10⁻16. These UB reports of evaluation of primary frequency standards are more in line with the scientific criticism on the first accuracy evaluation. At this frequency uncertainty, the Nist F2 is expected to neither gain nor lose a second in more than 211 million years.